So what I want to do today is let's go over the exercises that you did last week, or yesterday, and briefly. And I want to give the lecture for today and then turn to the workshop that you'll do next week. There's a lot of coding. Relating the coding that you'll be looking at to the lecture is extremely important. So I want to leave enough time at the end of the day to do that. Okay, so you're looking at these different types of heating systems, installation cost and operating cost. Just kind of quickly going through it. I imagine you've all done it. First of all, in the model with just installation cost and operating cost, what'd you get for the willingness to pay for additional operating cost? Actually, I've got, who's Galena? Is she not here today? Oh, that's right. She turned in hers, and so I was going to use hers as my crib sheet. I was going to ask if it's okay. What'd you get? 0.735. 0.735. So that means a person's willing to pay 75 cents about for $1 of savings in operating cost. Is that reasonable?
No.
No? Why not?
Because they get that dollar per year, right?
Right. So it's this model is clearly wrong. I mean, you really need to look at these things when you're looking at your models to see whether there's stuff that just doesn't make sense. If you take the inverse of that, you get a discount rate that's over 100%, meaning that people need to get a rate of return of 136%. Isn't that what you get? To be willing to invest $1. I mean, that's ridiculously high. And so you know something's going wrong. You can test the hypothesis that the actual rate of discount is 0.12, and you reject it soundly. Then you add the constants. Adding the constants makes actual shares equal predicted shares. That's one reason you add the constants. In this case, it also makes the willingness to pay or discount rate, whichever way you look at it, more reasonable. So what do you get as the willingness to pay after you've added the constants? 456. And that gives a discount rate of what?
22%.
42? 22, yeah. Thought so. 22%, 4.56. 22% is a little high. It's kind of like a little bit myopic. But I don't think it's unreasonable, particularly given that the people, who's making the choices here? It's the person who built the house, not the person who's going to live in it. So it's possible that the builder would be less concerned about future operating cost reductions than the person who actually lives there. And so they might have a higher than reasonable, somewhat higher reasonable than reasonable discount rate. So this is probably not out of line at all. You can also test the hypothesis. How many did that of whether 12% fits, even though it wasn't asked for? Well, you cannot reject the hypothesis that it's 12% in this model. So what it's doing here is these constants have made the model correct on average and has made your coefficients more reasonable. Why would a builder care at all about future operating costs? Because you would expect the buyers,
People buy the house.
Right. And there's going to be some translation to the buyers. The buyers are going to see this, and it's going to affect their willingness to pay for the house. There's, probably, if it were perfect, then if you had perfect capital markets going on here, then the buyer and the seller would have the same discount rates on equilibrium. But that's probably not perfect. So that's probably why this is a little bit higher than what you'd expect for a reasonable buyer. Okay. Then you add income. Instead of having just installation costs, you have installation cost divided by income. The reason for doing that is, as I said in the thing that in the problem set, that's a way of expressing the idea that people who have a lot of money are less concerned about the installation, the upfront costs. And so you want to capture that kind of systematic taste variation. So what did it do to the model? Make it better, make it worse? Well, did the log likelihood go up or down? Down. Well, so you got the same number of parameters and you got a worse fit. You would think this is just not a better model. Somehow the income of the household isn't entering in that fashion, if it enters at all. So then instead you tried to look at the issue of whether to put in income as a constant for each alternative. And just looking at the point estimates, first of all, what do the point estimates imply? What can you kind of learn from the point estimates about the way people value these systems? Is there anything?
Statistically significant. Statistically significant.
They're insignificant. But suppose you just look at the point estimates first. What do the point estimates kind of tell you, if anything? Before you decide that it doesn't tell you anything, if you're just reading the point estimates, what would you learn from it? Right. Rich people like central systems. As your income goes up, your probability of getting a central system goes up. What that implies is central systems are luxuries by the definition, old Econ 1 definition of luxury, and room systems are not. What's the opposite of a luxury good? Yeah. It's not inferior. I can't remember. Anyway, normal good, whatever it is. Your income goes up, you buy less of it. That's an inferior good. It's not Giffen. That's when your price goes up, you buy more of it. It's an inferior good. And that makes sense. So the point estimates are not out of line. It's just that all of these coefficients are highly insignificant. And if you test the hypothesis that the whole group of them enter, you clearly reject. You accept the hypothesis that all their coefficients are 0 simultaneously. So this isn't helping. So, how many people looked at other models? Did anyone find a model they liked that had demographics in it?
Operating cost, percentage of income,
How'd that work?
significant.
Huh?
Significant and negative.
Did the model end up fitting better than when you didn't divide? Because it's got the same number of parameters. I haven't tried that, so these are legitimate questions.
I don't think it was any better. It wasn't any better.
It wasn't any better? Galena did one in which she put in regional dummies, and it fit better, but not. She identified it as her favorite in her answer, but it actually, those regional dummies as a group did not enter significantly.
I entered in dummies for the North Coast. I know the mountain didn't matter, but for the North Coast, they had a preference for gas systems.
North Coast is more gas, yeah.
So
And that was significant?
It was significant.
How about you?
One thing with the reading the explanation of the data set, it seemed to suggest that the prices sort of incorporated regional characteristics.
They do insofar as we tried to create them to depend on the weather in the area and energy prices in the area. There are still regional differences. North Coast does have more gas than you would expect just on the basis of price, and I don't really know why, but that is a phenomenon that's out there. Mainly these demographics didn't enter. And there are regional things, but they're not really demographics so much. It looks like the characteristics of the household are irrelevant. That's not particularly surprising, is it? Because it's not the household that's making the decision. It's the builder that's making the decision, and they don't know who they're going to sell it to. They might know kind of an income group that they'd sell to, but certainly age is not something they would know, or other demographics. And so actually not finding results here is a positive finding. It's saying, you know, this is identifying more exactly who the decision maker is. It's not the household. And so again, it's important to learn when you're getting results and when you're not getting results from your model, and being able to interpret both kinds of situations. Now, forecasting. Did we do everything up to forecasting? Yeah. Okay. Here's the results I got. So this is gas central, gas room, electric central, electric room, heat pump, and we're going to add a sixth one later. So we start out with original. These are the shares before you do any forecasting, and you want to compare against them. So what we did was to subsidize the heat pump. This is actually a program that was going in California quite actively until deregulation. Now it might be picked up again, since deregulation is going the opposite direction of what anyone expected. The subsidy ended up increasing this from about 5.5% to about 6.5%. So, whoops. Is that what y'all got? 0.645? Did everyone get that? Good. So what this would translate to is an elasticity. This turns out to be a 16% increase, and we were decreasing costs by 10%, so that gives about an elasticity of negative 1.6. That seems pretty reasonable. Who in the hell has their phone on in here? I was at the symphony and a phone rang. I tell you. I was driving behind someone today talking on the phone too. They were, not me. Let's see. Okay, so elasticity, this seems pretty reasonable. What's interesting though is that, as you would expect, it draws proportionately from all of these because it's a logit model. So even though an electric system is, a heat pump is an electric system, it doesn't draw much from the electric systems because they don't have much to start with. It mainly draws from gas central. That's highly unlikely. Even though these are small percentages, you'd still expect more than proportionate amount to come from these other electric systems, since this is an electric system in itself. So this kind of pattern, actually, if you're, this IIA problem, it's important to recognize, this IIA problem is not a problem if all you're trying to forecast is the share of the thing that you're concerned about. It only really affects the substitution patterns. And so you could get this share pretty accurately, even though where it comes from is not accurately predicted. So again, when you're trying to decide whether to use a logit model or not, you want to know what you're going to use it for and whether you care about substitution patterns or not. If you don't care about them, just going after the absolute share, you might actually end up better here than with a more complicated model where there's more issues going into this prediction of the share itself. So then a new technology. What are we calling this? This new technology? I got about a 10% share. Is that what y'all got? Yeah?
When we forecast a new technology, we must give an estimate for the specific effect.
Yes.
Which one would you use?
I use this one. Since everything else was being kind of going off this electric central, I use that. But you raising an important question. Whenever you're adding a new technology, you got to figure out what alternative specific constant to give it. And it might be that it looks kind of similar to one of the other ones, and so you choose that. It might be that you don't think it's similar to any of them in the average of unobserved factors, and so you'd want to make up another constant. This is a real issue in all of forecasting, but it becomes really clear when you do discrete choice. It's true with regression too. But essentially, by choosing your alternative specific constant, you're determining your forecast. So the question starts becoming how much are you forecasting and how much are you putting into this model.
If you didn't put in an alternative specific constant, would that totally throw off your answer?
That is an alternative specific constant of 0. You can't not put it in. You're making a decision then that the impact of all the unincluded factors is 0. And you can do that. What's useful here is try to think of reasonable alternative specific constants and see what they translate into after all the other stuff in the model is incorporated.
Are you going to give out some sort of code or something just so we can check our, if we didn't get it right, just so we can figure out how we...
Well, I wasn't planning to. I did run all the models and I've got output for them. Let me think about that. It just means a lot of copying.
Oh, sorry.
That's okay. I could put the outputs in the account. Yeah, I've got them in mind, and then it would just be writing it over to the central account. That's an idea. Let me talk to Grace about doing that. Okay. Any issues on this?
What constant did you use?
I used the constant for electric central just because we're tying all the variables back to that one. It's kind of an electric central system that was, had different cost characteristics. But again, you could. What did you use?
I used 0 and I got like 2 or 3%.
Yeah, that's what I get.
Yeah. Okay. Well, that tells you something. Anything else? Yeah. No, these were annual costs. The operating cost was on an annual basis, as I recall. It's written in the README file, but I'm pretty sure it was annual. What? The discount rate in the first model was extremely high, ridiculously high. But when you put in the constants, it went down to 22% discount rate, which is not that high, particularly knowing that this is the builder instead of the owner. And that the capital markets are not perfect. That's not an unreasonable level. Yeah, last.
I have a question with these alternatives to the constants in your book. It says like then we won't have the red box problem. Now if we predict we still have that problem, how is that exactly? I mean, it still draws proportionally.
The new book I'm writing is de-emphasizing that aspect of constants. If you saw that within context, there was an example of the Mother-Logit theorem in which you can express any model as a. The way it actually fits is. How would I do it here? There's a way. Essentially what it's saying in a deep sense is completely trivial. It's like the deeper you get, the more you realize it's a trivial concept. You can find constants for these that'll give you any pattern of change. You change the constants. This will give you any pattern of change for these. And hence, what that's saying is by appropriate choice of your constants, rechoice of your constants, you can get any pattern of substitution. That's not a useful result, but it is true, and it's an example of the Mother-Logit theorem. Now that we have models that can explicitly deal with IIA, we don't have to find ways to contort Logit models to handle the issue. We can instead go to a model that does it automatically. That's a good point, though. An embarrassing one, but a good one. Okay. Now what I want to turn to is you used SST to do the estimation this time for this Logit model. What you will probably be doing when you're doing your own research is actually writing your own code to write models that are specially made for your situation. And to do that, you'll end up needing to do some form of numerical maximization. Practically all forms of estimation can somehow be put into maximization terms. Maximum likelihood is maximizing the likelihood function. Method of moments, where you have moment conditions. You take the square of those moment conditions. That gives you a function that you then minimize or maximize the negative. So generally, you will end up wanting to write programs that do maximization on your own problem. So what I want to do now is talk about how that's done numerically. That's the point of today's lecture. And then in the problem set, use the same data that you're using now, and yet use your own codes to do maximization instead of SST. This is extremely important. A lot of the models that we are studying here, including Probit and Mixed Logit, have already been written into software. And so if you're just wanting to use them as is, you actually don't need to know any of this coding issue. But I imagine you'll find whenever you start doing your own model that you'll want something that's slightly different. It's got a scale factor that's done differently than what the code allows or something, and so you'll be wanting to write your own stuff. And in fact, this is what I hope you'll do. This is the value of simulation. It allows you to tailor-make your models. And so now that we're in this age of simulation, you don't want to then start feeling constrained by what's in the programs, canned programs, and what's not. You want to know how to do this stuff on your own. So the issue now is how to maximize a likelihood function. Let's say we're just using that to maximize. So notation over here. The log likelihood function is a function of the parameters, and it's the sum over all observations that you've got, just in general terms, of the log of the probability of that nth person's actions, whatever that person or decision maker end up deciding to do. Actually, leave that, denote that that's dependent on the variable, on the parameters also. I'm stating this as a function of the parameters because what we're wanting to do is find the parameters that maximize this function. So the fact that the probability depends on the data and all that other stuff, that's just being suppressed. From a pictorial point of view, what we're trying to do is find the top of this log likelihood function. As you know, it's going to be negative, as we discussed last time, and we're wanting to try to find the top. So some more notation. The gradient vector. Remember, throughout doing this, you've got to really keep care of the dimensions of each of the elements we're talking about, whether it's a vector or a matrix. We'll see there's a gradient matrix that is different from this. They're related, but when you're coding, you got to know which one you're using. So I'm going to denote this GT. Let's start here. Suppose we're at a particular point, beta t, on this function, and we're trying to find out how to reach the maximum or how to move towards the maximum. So we're going to use information that's available in this part of the function to get an idea of how to move towards the maximum. Okay. So the gradient vector at this point is the derivative of the log likelihood function with respect to the parameters evaluated at the value, the beta that you're at. Okay, this is a column vector. We're always having vectors as columns, and so the derivative with respect to this is a column vector. It's k by 1, k parameters. Then the Hessian, it's a matrix, though the Hessian is always a matrix, and so you don't have to call it that. It's the derivative of the gradient vector with respect to the parameters, which makes it the second derivative of the log likelihood function. So the first derivative is with respect to the column vector. The next one's with respect to making it a row vector. That is the derivative, second derivatives. I'm sorry. That's right. Or you can express it as the derivative of the gradient with respect to that. And this is k by k. Okay, so it's the matrix of second derivatives. Okay, so whenever we're at a particular point, for the procedures we're going to study today, they all take the same form. You move from this existing point to a new beta that's hopefully closer to the maximum, okay, using a step beta x plus 1, that's your new point, is equal to where you originally were, plus that. This is a scalar. It's 1 by 1. This is the gradient vector, so that's k by 1. And this is a k by k matrix. And the procedures will differ in what they use as this k by k matrix. Okay, so all that's just introduction. I'm now going to motivate why you would want to take a step like this, what various useful values would have for this k by k matrix in the middle, and what that whole form looks like. But for now, I just wanted to write it up there so you'll see it coming up in the different forms. Okay, suppose you're here and you want to find the value of the next beta, beta t plus 1, that is your best guess at the top of this hill. Okay, so you want to move as close as possible, make as good improvement as possible to the top of the hill. If you do that, then you end up employing what's called NewtonRaphson procedure. And let's just derive what that is. Let's take a second order Taylor's expansion. It's important to remember when we're taking second order Taylor's expansions and when we're taking first order. This time we're taking a second order. Okay, so we want to take a second order Taylor's expansion of the likelihood, log likelihood at the new value around what it was at the first value. So we know it's wherever we are now, okay, plus whatever distance we're going to move. These are row vectors, so we prime it to make it, these are column vectors, so we prime it to make it a row vector. Multiply it by the gradient vector, which then is essentially saying go in the direction of the slope by whatever distance is between them. Plus then the second term, second order term, this is the Hessian. Okay, so that's the second order Taylor's expansion. What it means is that it's an approximation that is good as long as the slope and the curvature give you valuable information. When you've moved far enough out to where those no longer provide valuable information, then it's no longer a good approximation. So the idea is to maximize this. Find the beta x t plus 1 that maximizes the likelihood function. So we want to maximize this approximation. And we do that by taking the derivative we're finding the new value that maximizes the likelihood function. That drops out because it's a constant. This is simply the new value times the gradient. The derivative of that is the gradient. Plus this is 2 times a half. This one drops out. Set that equal to 0. Rearrange, take this over to the other side. And then divide by this. And move that to the other side. That gives you bt plus 1 is equal to beta t minus ht inverse. Okay. So another way to look at this that I think is easier is always do a plus. You're kind of moving a step. You're going somewhere. Okay. So the NewtonRaphson procedure, which maximizes a second order Taylor's expansion, okay, to get to the close to the top, okay, uses the scalar is equal to 1, and this matrix is equal to the negative of the inverse of the Hessian. So you calculate the Hessian, take the inverse of it, take the negative of that, and that gives you this matrix. Multiply that by the gradient, and that gives you how much you move. Okay, now why does this make sense? This should make sense aside from this. Knowing why you do it is important. It's because you're maximizing the second order Taylor's expansion. But it makes sense intuitively also. Suppose that this thing is positive, as we'll see it is in good situations. The first thing you note is that you're moving in the direction of the gradient. So if the gradient is positive, you start out at b to t and you move in a positive way. On the other hand, if the gradient's negative, you start out at some beta t and you move backwards. So you're moving in the direction of the gradient, as long as The Hessian's positive, as you'd expect. Why, though, do you divide by the curvature? You can look at this as being slope divided by curvature. The slope is the gradient. The Hessian is the curvature. Why do you divide by the curvature? Has anyone got an idea? This also makes intuitive sense. What's happening here is, let's compare two different situations. Where you're at a place where the slope's the same, but here the curvature is very small, and so there's not much change in slope. And because of that, you have to go a long ways to get the maximum. On the other possibility, we've got the same slope here, but the curvature is enormous. So the slope is the same as here, but the curvatures, the change in the slope is enormous, and the maximum is going to be real close by. So here you've got a small curvature. Divide by a small number, it gives you a big number. So you're taking a big step. Here you've got a very large curvature, and hence dividing by a large number gives you a small number, and so you take a small step. So in both cases, you're moving in the direction of the derivative, which is what you should do to go up the hill. But how far you go is determined by the curvature. If you've got a lot of curvature, you know you don't need to go very far to get to the top. If you've got a little bit of curvature, you need to go a long ways. So this formula is not just some kind of magic. It really has intuition behind it. And it's important to realize that when you're maximizing your functions. Okay. There are 3 points to make about this. First of all, if your function is quadratic, if the log likelihood is completely, perfectly quadratic, the NewtonRaphson will reach the maximum in one step. You can work this out yourself, prove it to yourself by taking a first-order Taylor's expansion. Express the likelihood function as this. Find the maximum of that function, and then show that this step, using the Newton-Raphson step, will bring you to that immediately. So it's kind of tedious proof, but it's very easy conceptually. What that tells you, another thing that tells you, is that you can always think of a step as being the step that moves to the maximum of the quadratic that has the slope and curvature at the point that you're at. Okay? So when you're knowing what this process does is important for when it fails, you'll know why it fails. Suppose you're at some point here, you've got a slope and a curvature. If you just continue that out as a quadratic, the Newton-Raphson will take you to the top of that quadratic. So wherever you are, the slope and the curvature define a quadratic, and the Newton-Raphson will take you to the top of that. Now, that's not going to be the top of your actual function, because your actual function is probably not quadratic. If it's not quadratic in the sense, it could be like that, so that it has the curvature at that point is not continued. It becomes less curvature as you move further out. So you're wanting to move here, or it could be the other direction. But you always will realize that what you're doing in each step is moving to the quadratic, the top of the quadratic that has the curvature and slope at that point. So then this raises the second idea with Newton-Raphson, the second point. Notice that the pure Newton-Raphson has the scalar of equal to 1. There's nothing here in front of this Hessian. Okay? Nevertheless, you might want to set that scalar to something other than 1 for reasons that we'll see. This is one possibility. Let me get to that one in a second, because it's easier if you start with this other one. Suppose you have a situation where you're at a place, the curvature and slope give you a quadratic that's maximized there. So Newton-Raphson is going to move you Sorry, let me start over. Let's say it goes like this. And the quadratic is maximized here. So NewtonRaphson will move you to that point. This is the quadratic that has a slope and curvature. But suppose your actual function looks something like this. Okay. Then what's going to happen is you start out at this point. NewtonRaphson is going to bring you